Good afternoon. Okay, I'm happy to see you so excited to come to CHEM 1A and also so awake because today is daylight saving. In the morning it was pretty difficult for the students and for me because everybody was an hour early. And so let's get right into it. The last time we talked, if I could have your undivided attention, please. The last time, we talked about thermodynamics, and we've seen that the energy of the universe is constant. We neither do gain energy nor do we lose energy. If you gain energy in a system, then you lose it in the surroundings. And if you lose energy in a system, the surroundings, that energy will go to the surroundings. So we looked at thermodynamics, and there we defined a system and the surroundings. And we actually looked only at the changes between system and surroundings. We didn't talk about absolute energy changes because that's very difficult to do. And we're going to continue that by not looking at absolute energy changes. So we've seen that the change of energy can be expressed as heat and work. And energy is a state function. It only depends on the initial and the final state, and I demonstrated that to you by going up and down the stairs here, or going to Denver directly, or in a very strange way. So this is a state function, and heat and work are not state functions, okay? They depend very much on the direction and on the way we get there. So the change of the energy of the whole universe is the change of energy of the system plus the change of the energy of the surrounding. And the change of energy of the universe is constant, and the change is zero. If you take the system changes and the surrounding changes, they have opposite signs. With this will become zero. So we talked about, can I have the microphone a tiny little bit louder? Tiny little bit. I gotta rock them. All right? So we had the system here, and we looked at it as a gas, for example, an ideal gas, and we have the surrounding. And we had the definition: if heat comes out of the system, its internal energy goes down. And with this, we have a negative sign on the heat. If I put heat in the system, what happens to the internal energy of the system? It goes up. Does the temperature go up? Yes. Of course. The energy is directly proportional to the temperature. And so we have decided this. Now, the system, or that gas, can do work. If it does work, does the energy go up or down of the system? It does work. If you do work, does your energy go down or up? Down. Very quickly so, okay? It goes down, all right? So if you do work, if an outside pressure does work on a system, does the energy of the system go up or down? Up, okay? Now, if I want to do the same thing isothermal, that means I'm not changing the temperature of the system. So if I expand, the gas does work. So does the temperature go down? Yes, but I don't want to allow it to get it down. It should stay the same temperature. What has to happen? Heat has to flow into the system. And the same with the reverse sign is true. If you do work on the system, the energy goes down and the temperature goes down. But now I say, no, I'm not going to allow that, so heat has to flow out of the system, all right? That's what we have defined here. If the system does work, it's negative. If work is done on the system, it's positive. We already talked about this, essentially, the work of gases, and this was isothermal. And then we talked about adiabatic. Adiabatic means I have this system so insulated from the surrounding that there is no exchange of heat possible, okay? With this, the Q equals 0, then the change of energy is only the work. Now, if you compress the system from outside, what happens to the energy? Goes up, exactly. That's this case. And the reverse, if the system does work, what happens to the energy? The energy goes down because we don't allow exchange of heat. So I'm asking you a question now. Think of a rubber band as a system. When you stretch it, you do work on it, don't you? And when you release it, the molecules go back. And I'm asking you, you have a stretched rubber band and it's suddenly released. What happens to the temperature of the rubber band? Does it increase? Does it stay the same? Or does it decrease? Why don't you think about it and give me your answer? Did you get some gloves? Okay, everybody. You have no glove? Rubber band. If you don't have any gloves, raise your hand, please. One glove is enough. Nada. We need some on this side here too. Down here and over there. Very polarized, you see that? All the negative, not negative charge, all the polarization is over to there, okay? So that's the, both of them are over there. Now we are depolarizing. So let's have a look. Yeah, that was to be expected. Why don't we do that experiment? Equal amount of people say, you take that glove. I wait for another 15 seconds till these guys have one, and they're in the front there. Give me a couple of gloves. Give me a whole bunch. Okay, thank you. You give them to them here, okay? All right. That's mine, the other one. Okay. Lots of snapping going on here. Don't hurt yourself. There's one more. We need one more. Sorry. You have one more? Okay, let's go for it. I don't have forever, unfortunately. So you take that glove. Listen very carefully. Yeah, hi. You take that glove and take the index finger, okay? The index finger, hold it at the root of the index finger, like this. Careful, they're dirty now. Ready? Now you expand it very quickly and hold it. Hold, hold, and hold. Okay? So, hang on to it. Don't stretch it anymore. Now use your lips as a thermometer. Use your lips and feel them. Now you have sort of gauged what the temperature is. Now you, careful, listen careful before you do it. Now you release them and then immediately put it in front of your lips again. Why don't you answer that question again? Pull it, hold it, hold it, hold, release, and put it on your mouth. What? Yeah? No snapping anymore. Clicking, not snapping, clicking. I'm glad that you guys are awake. That's, you can do the opposite. I show you in a minute. Excellent. I think we need to cut this short here. Everybody in? Click in, click in. Okay. All righty. See. So, let's do the opposite. Let's do work on the glove. You pull it quickly and immediately hold it in front of your mouth. Hot, huh? Yeah. So you did work on it. It was adiabatic. That means it couldn't escape the heat, so it felt hot. Now you let it come to equilibrium with the surrounding. Now you let it go and feel it. Now the glove, the rubber band, did work on it. It pulled the molecules together, and with this, the temperature, we didn't allow exchange. Now it's the exchange of heat again here, but it was so fast that the heat couldn't exchange. The same like with the fire extinguisher I showed you before, adiabatic expansion. And so this was the stretching, and then it is released. So it did work, the rubber glove. With this, there's no heat exchange. The change is the work, in energy is the work. And the system does work when it pulls back together. And with this, W is smaller than 0. And the temperature decreases. And this was the right answer. Okay. So today, we're going to look a little bit more at thermodynamics, and we look at it, we try to explore what we can use it for. So we have learned that if you have constant pressure, which you have here in this room, and you want to do a chemical experiment on the bench top, we have this new state function, H, the enthalpy. And the change in enthalpy, if there's no volume change, is just the exchanged heat, because we have constant pressure. So if you look at the chemical reaction, you have an exchange of heat possible. And the heat can flow either in or can flow out of the reaction. So we had this here. This is the surroundings. This is our system. That's our energy scale. So you have heat flowing in. With this, your system has a higher energy. Okay? This would be what kind of a reaction where you need to flow in heat? Would it be exothermic or endothermic? That would be endothermic, exactly. Q is larger than 0, and with is the change in enthalpy is also larger than 0. Now, the opposite case is, of course, if you have it at a higher state, the system, higher energy state, and it goes to a lower energy state, there it goes, heat flows out. Remember, hydrogen and oxygen was at a higher state, the reactants were at a higher state, hydrogen and oxygen, and the water, the reaction product, or the product, was at a lower state. So it went from this state to that, so the difference was given off in heat. So this was an exothermic reaction. You could also think about a reaction where you have, I don't know, any hypothetical reaction, where you have some products, and the reactants are up here. So you would have to have heat flowing in to get up here in energy. So this would have more energy than that then. So that would be great if we could take the heat of the reactants and the heat of the product and compare them to each other. And then if there's a difference in energy, it could be negative or it could be positive, then we know it's exothermic or endothermic. So with this, we do these calculations when we use our shielding. If it's negative and a large negative number, we put a huge shield in front of here. If it's positive, we are not worried about it, okay? It's going to happen, but it will suck some energy out of the room, but not so much that you're going to be in danger. But if it releases energy, then we need to have a shielding. So we could calculate that, and this is what we're going to look at today. So we do these calculations in standard state. We say, and this is a funny thing, we say all the liquids are 1 molar, and all the gases have 1 atmosphere, are at 1 atmosphere, and we use 289.15 K, that's 25 Celsius. This is our standard state. And we compare them in standard state with each other, and this is sufficient enough to tell us if this is exothermic or endothermic. And these standard states for these individual reactions, the enthalpy of formation of A and of B and of C and of D, you can look up in your book in the back. There's a large table there where there's for all kinds of compounds. So let me ask you a question. We have the reaction enthalpy change at standard state for the reaction where we have liquid water at 100 degrees goes to liquid gas at 100 degrees. And this is an endothermic process. To go from here to here, it's an endothermic process. Which is most hazardous at 100 degrees? Is it the water, is it the steam, or the water and the steam combined? Why don't you think about it? Which one would have more energy? That's probably the most hazardous. And give me your answer, please. So there's an energy, 44 kilojoules per 1 mole of water to 1 mole of gas. It's plus, it's endothermic. It's even nicely animated. Boiling water. Maybe some of you will remember your mom or your dad when you cooked your pasta or noodles and you drained the water off. I bet you many of you have gotten that steam in the face. And your mother said, beware of something. Beware of the water. No, that's not what she said. No, we don't want to do that. That's going to be interesting. Let's see who that is. Right answer, though. Right answer, though. That's the one. Okay. So you listened very carefully, and you said that the steam is most hazardous if you get steam on your skin. And I do agree with you. And the reason is that the steam has 44 kilojoules more heat in it. Okay, compared to the water, to the liquid water. That means in order to go from water at 100 degrees or 212 Fahrenheit, 200 degrees Celsius or 212 to steam, it has to pick up 44 kilojoules per mole. So with this is much more energetic. It has more energy, so it burns you more, and then it goes down to water, and now suddenly you have 100-degree water on your skin, okay? And this burns it the second time around, all right? You get burned twice, so to speak. All right, so you got this idea. Now let's see, let's do another one. You have propanol and isopropanol, and you know by now what isomers are. They have the same molecular mass, the same number of atoms, same kind of atoms, and you have here 3 C's, here 3 C's, 6, 7, 8 H's, 3, 4, 5, 3, 6, 8, and 1 oxygen. Okay, same. But the isomerization to go from propanol to isopropanol is endothermic. Which burns cooler? The propanol, the isopropanol, or they are just burning? It's the same. Why don't you think about it? Which one burns cooler? Same principle that I explained to you earlier with the water and the steam. There's no discussion yet, actually. You guys are on fire today, huh? Sleep deprivation. So the propanol burns cooler. I agree with that. Why? Let's think about this. Why? So this has a certain energy, okay? An H, enthalpy of formation. To make this, you have a certain energy. You need a certain energy. To make this, you need to put in some extra energy into that. So which one has more energy? This one, okay? That flame will be hotter than this one. It will have higher energy than this one. And with this, so this is, what does it burn to? It burns to, that's a hydrocarbon, it burns to CO2 and water. So the hydrocarbon is propanol, that's our reaction here. It burns to CO2 and water. It will release energy. It releases it's a negative enthalpy term. That means it releases heat. Delta H is negative. And now I make propanol. In order to make isopropanol, I have to put in some energy. Okay? So I had this energy here, and I put in extra energy to put isopropanol. But isopropanol, to make isopropanol, but isopropanol also burns to CO2 and water. So it goes down to here. So which one will burn hotter? This one here. Okay? So with this, the answer, it was the question, which one burns cooler? This one burns cooler than that one. And this was the right answer. Why don't we do an experiment? So remember, we needed 44 kilojoules per mole to go from water liquid at 100 degrees or 212 Fahrenheit to water gas, which is steam, all right? So there's a lot of energy necessary, 44 kilojoules per mole, to do that. Now what we're having here, we're having isopropanol, and we put in a towel into isopropanol, a paper towel. Okay, Karen is soaking this with isopropanol, and then she will burn this. And is this camera, which is this camera here? Okay. So she will burn this. Oh, it's a very hot flame. You can feel it, how hot it is, isn't it? Oh, very hot. Okay, very dangerous, very hot flame. So she burns it now, and so, okay, there it goes, and it burnt the paper in the process because it was so hot. So now we take a mixture of 50% water and 50% isopropanol. So we have water and isopropanol, and the isopropanol will burn, and we do that. Let's see what we can do with that. You see that? It's not so hot. See the steam? It didn't burn the towel. Okay. How come? Because the energy that was released by the propanol burning was picked up by the water, and the water was heated from room temperature to 100 degrees and then to steam, and it cooled the towel down. With this, you have a perfect towel. You can do this also with money. You can do this with not with 5. No. Let's see. Let's have a good good one here. And so, Karen, let's do that with a $1 bill. You can do this at parties, but be careful of the fire alarm. Okay. And it was so cool that I could touch it, actually, the flames. There you go. She's burning my dollar bill here. See that? There it is. Magic. Okay. Thank you, Karen. So we'll be playing with heat exchange today. And so you've seen that we have the differences between the enthalpies of the products and of the reactants and the product. And if it's negative, it's exothermic, and if it's positive, it's endothermic. We have known this since quite a while. So we need to find a system that we can find what these compounds is. What is A in my reaction? What is B in my reaction? A is some kind of a compound, B is some kind of a compound, makes C, and it makes D. So if I would know these enthalpies of formation for A, and for B, and for C, and for D, if I would know that, then I would be able to calculate the difference between them. I take the sum of the products minus the sum of the reactants, and what I get out is either negative or positive, and with this I can say there's energy released, it's exothermic, or there's energy necessary for that reaction, it's endothermic. So how do we do this? This is all relative to each other. We don't need to know absolute number, but we need to have relative numbers because we are just comparing relative numbers with each other. So what we say, the elements in their standard state are used, and standard state are used to make compounds. And this is the standard enthalpy of formation at standard state. So if I say standard enthalpy of formation at standard state, that means it is at 1 atmosphere or at 1 mole, and it is at 25 Celsius or 293.15. No, 98.15, I'm sorry. So what could happen is, these are the reactants and these are the products. So first I need to know what is the enthalpy of formation for the reactants. So I would go, in this case, I could go up the hill, energy hill. Is there a slide missing? Yeah, this was the one I wanted. I didn't talk about this yet, okay? The elements in their standard state, and so I make a compound, and in order to do this, I need to put in heat. So the enthalpy of formation in standard state of that compound would be positive. That means in order to make that compound, it has to go up energy hill. Yeah? So that would be a positive number. And if the other possibility would that I have the elements in their standard state, I make the compound, and this would release energy, and this would be the enthalpy of formation of that compound would be then negative, which means there would be energy released. So what's going on? What are the elements in their standard state? What are the enthalpies in their standard state? Actually, elements themselves in their natural state, let's put it natural state, they have the enthalpy of 0. For example, carbon, solid carbon, as graphite, has the enthalpy of 0. Aluminum has 0. Iron has 0. And now hydrogen comes diatomic, okay? So H2 has 0. N2 has 0. And Oxygen I did already. No, O2 has 0, okay? So this is what we have agreed upon in order to make this relative measurement. And then people measure these, they put oxygen and, for example, hydrogen and oxygen together. Hydrogen is 0, oxygen is 0, and then they measure the energy change when they make the water. And people have measured all this, and this is tabulated in the back of your book. There's the standard enthalpy of formation, okay? And so now with this, we have the tools to calculate our reaction enthalpy. What energy is released when I do this reaction? So I take the reactants. I have, for example, CO2 and water. So I get the standard enthalpy of formation for CO2. I look it up. The standard enthalpy formation of water, this would be in this case here, CO2 and water, would be in, for example, the products. What would we make? We can sort of react oxygen with some sugar, for example. Yeah? So we would look up the standard enthalpy of formation of that sugar, get that number here. Standard enthalpy of formation of oxygen is 0. And with this, we have now the number for the reactants. So we take the sum of the enthalpy of formation at standard state for the reactants. And don't forget, you have the stoichiometric factor goes in the front here for each of them. Yeah? And then you react the reactants to make the product. So there's some energy released. And this energy we want to calculate. So we take the product. We know this was in our case water. CO2 and water. So we look those up, CO2 and water. So we get the delta, the standard enthalpy change of formation for the products. That would be CO2 and water. So we take then the change in enthalpy. This would be the reaction enthalpy for this reaction would be the sum of the, and the stoichiometric factors have to go here, of the energy of formation, the change in enthalpy of formation for the products, minus the sum of the change in enthalpy of formation of the reactants, okay? So that's that simple. You probably did this in homework already. Or is it going to be in homework this week? This week, okay. Good. And so that's all there. And this is actually, that's why we went through this whole state function business. Because I could make a state function. If I have a circular process, I go here. I know this number. I know this number here, how much it goes from reactants to products. Then I can reverse this. So this plus this should give plus this in reverse. If we go to this direction, back to the standard state, that should be 0 then. Then I have a perfect cyclic reaction. So these are the standard enthalpies of formation, and there are many, many more. So this was, for example, for hydrogen and oxygen, gas form, bimolecular, and nitrogen, it's 0. For graphite, aluminum, and iron, it's 0. Now, if you go hydrogen and oxygen gas, they have positive enthalpies of formation. Why would that be? You have H2, that's 0, but now you have to make an H out of it. What do you have to break? Yes, and if you break bonds, what you need? Energy. Okay, excellent. And so that's with that energy that you need to break that bond between the two hydrogens. That's exactly that energy, and here is that energy. So if you have carbon as a solid, you want to make carbon gas, so you need to put in energy. That's why the carbon gas has plus 717 kilojoules per mole standard enthalpy of formation. Now, remember, we have water. It was exothermic when we made this, minus 286 kilojoules per mole. This was the liquid. And then we had the gas form, which was the steam, minus 242. Now, if you go from gas to liquid, what would that be? The difference between the two, okay? And this would be plus 44. Remember, we had plus 44 in the chem quiz. That makes the difference. CO2 is minus 394. Alcohol, for example, to make alcohol, ethanol, you need 200. You release 278 kilojoules per mole. If you make sugar, sucrose, I think, you release 1,274 kilojoules per mole. This is a huge, huge energy. And if you have this here, iron, you make 824, aluminum oxide, it's 1676. So let me ask you a question. I actually said it already. What is the delta H of reaction for the oxidation of iron? So iron and oxygen gives Fe2O3. What is that? Obviously, it must be exothermic because there's only negative signs here. And so is it minus 575, minus 824, and minus 1073? Why don't you think about it? Give me your answer. No. Ah! It's Monday. Why don't you give me your answer? At least you have a quick look. Give me an answer, but you need to understand why. This is different. Oh, good. Why don't you click in all? Click all in. Just click anything. 244 we were or something, 270 actually. Click all in. Everybody in? Good. So now let's do the real thing here. We don't want to display this. So now I go back. So. Why don't I give you 30 seconds and you give me the right answer? Okay? Why is that? The answer that you're going to give me. You need to know why. Technology is unkind to me today. Or I'm unkind to technology. Okay, let's see how we're doing. So I guarantee you, lots of guys clicked something else. Or women too. No, they clicked the right. They want to have it right. Okay, good. So why is that? So you could look at this here. What's the enthalpy of formation of this here? 0. What's the enthalpy of formation of this here? 0. So that's actually, that reaction is actually the enthalpy of formation of iron oxide. Fe2O3, and this was written right here, minus 824, okay? So this is 0, this is 0. When you combine them, you get a release of 824 kilojoules per mole, and with this, the answer was that. So let's do another experiment. I've been told there are states in the United States where they have this white stuff on the ground in the cities, snow, okay, snow, and so it causes all kinds of havoc and with the driving, and then it becomes ice. So they put salt and sand on there, and it's very hard on the cars. And so the cars are made from iron, and they do rust. Then they look pretty rusty, especially if you come towards the East Coast, where there is a lot. Or Denver, for example, there are pretty rusty cars you can see at times. And so what is rusting? Is the reaction, that was iron Fe2O3 is rusting. The reaction of oxygen with iron to form iron oxide. It's an exothermic reaction, but it goes very slowly, okay? And it goes fortunately it goes very slowly, otherwise you would lose your car in an instant if that would be a very fast reaction. So let's speed this up a little bit. Let's use some liquid oxygen and some iron. This is what are we using as iron here? Steel wool. This is steel wool. Okay. You see the steel wool? Yeah, here, steel wool. Okay. Anybody knows what that is? Never used steel wool? This is very fine steel, how you call this? They are sort of shavings, you know. They're very fine. And your Brillo pads, for example, have that in there. No commercial. They don't pay me. All right? So we have the liquid oxygen here, so we got to give it a little bit of a kick in terms of energy to speed up a couple of these iron atoms to have come across the activation energy hump. So let's heat it up and then have a very close look. We do some very quick rusting now. We make an iron oxide. Go ahead, Karen. I hope this doesn't happen to your car, so keep it away from liquid oxygen. All right? You see there are some brown sprinkles on here, which is the iron oxide. That's the brown. Rust is brown. You all seen rust. And there it is. And it was a very quick rusting. Fortunately, it doesn't happen with our cars that fast. So, given what you know now, I'd like to ask you another question. Also related to iron oxide, but very differently related. You have iron oxide, and you want to mix it with carbon or iron or aluminum, okay, solid, shavings of it. You mix it, and it will react to form another compound, and it will release so much energy that it melts that iron oxide that you have to begin with. It melts it, and I want to know from you what kind of a compound that should be. So you need to look up here. I hope you can see it. And think about it. What could that be? Obviously, it has to release some more energy than iron oxide. That it can even melt the iron out of the iron oxide.
Do we get to burn anything in our lab this week?
I don't know. Didn't I talk about the beginning about borax, that you're going to do the borax this week? Yeah, this week's lab is a little bit ahead of me in terms of what you need to know, so you need to read the book a little bit. I'm trying to really keep it as parallel as possible, but sometimes it's not possible, okay? What do you need? So there's a majority, a large majority for C. Okay. So I need 31% need a direct explanation. Probably C also needs a direct explanation. Let's do that then. So, let's see, what's this here? Okay, we have iron oxide, and in order to make iron and oxygen, the standard, we have determined this already, the enthalpy of formation at standard state is minus 824 kilojoules per mole. But if you use aluminum and oxygen, you get minus 1,677 kilojoules per mole to make aluminum oxide. So now, this will be released if you have aluminum, and if you mix this with iron oxide and have aluminum and let this react with each other, it will make aluminum oxide, but will release this additional energy here. You see that? That's all the the energy that you have available from that reaction. So this will be, the sum of those here, will be minus 852, okay, minus 852 kilojoule per mole, and this will melt the iron, all right? All this extra heat. It's called the thermite reaction, and it's actually used still today in order to weld together railroad rails. So they put a form around it, put that mixture, it's called the thermite mixture, in there and ignite it, and then it reacts, melts that iron, and they take the form off, and it's cold, and they grind it, and they have a perfectly welded rail then. So let's do that reaction. If I could have the first two rows, please move out here. The first two move. You can stand over there. Take your stuff with you. The first, I need to protect you, okay? So, Okay, just move on to the side here. So I will explain to you. No, not dark yet, not dark. I need to tell them. Careful, don't hurt yourself. Okay, let's go. Come on, I gotta get this on the road here. Okay, so obviously, we did the calculation. And this is minus 800 kilojoules. That's a lot, okay? And minus 800 kilojoules per mole, minus 8 something. So we have a pot here, and this is a clay pot. It has this mixture of iron oxide and aluminum in there. And we have a fuse here, and the fuse is magnesium. What happened? The fuse is magnesium, and this is how we started. We light that fuse, and then we get the reaction going. In the bottom of this clay pot, there is a hole in there, and we put a little bit of aluminum foil over it that the mixture doesn't come out, okay? So that hole that you will have to watch that, because the molten iron will flow right out of the bottom, okay? And let's see, that's a nice reaction. Let me get the fire extinguisher here, and let's do, oh wait, I need my safety glasses. Okay, let's go. So Karen lights the fuse now. A little bit to the bottom also with the shot, and she's changing. Okay, fine. There it goes. That's the reaction. Now, did you see the coming out in the bottom? Okay, the molten iron. If you can have a shot of the molten iron now. Did you see it flow? It flowed right out of the bottom. And it's so bright you can see it. It's 3,000 degrees hot. And the iron came out here and dropped into here. Take a look when you go home, or when you are done when we are done here, which we actually are, if you can have the lights back on. And I see you on Wednesday. But don't touch anything, please. Thank you, Karen. Thank you. You've seen it in Chem 1A.